So you were talking about things from the 70s and 80s. There'll be a lot of remnants of that in this talk today. So I apologize to those of you who've heard some version of this before. I think I spoke on a preliminary version of this result in the logic workshop at City University a number of years ago, but the result's better now, so I'm happy to have this chance to talk about it. Okay, so we start with the idea of an integer part of a real closed field. Let K be a real closed field. An integer part is going to be a discrete ordered subring. So discrete means that there's nothing between 0 and 1. And it's an integer part of the real closed field if for any element of the field, there's an element of the ring that's within distance 1 of it. Okay, so it sits like the integers sit in the reals. The relevance of this to arithmetic comes in this old result of Shepherdson's from the 60s, that if K is a real closed field and R is any integer part, then R models open induction. So induction for quantifier-free formulas. So I'm going to be careless today in confusing the positive part of a model, a model of arithmetic with the ring it generates. Okay.
Dave, do you want both less or equal in the definition? Yes, maybe.
Well, I can change. Yeah, it would be okay to change 1 to less than. Yeah, I mean, it would be the same. Okay, and the second thing was that any model of open induction is always, there's enough induction there to show that the fraction field is dense in the real closure, so that the ring itself is an integer part of the real closure. And this theorem of Shepherdson is used in a lot of the results. Time you try to prove independence results about open induction, it's used by constructing some complicated real closed field with an integer part. A question that I think Angus and I asked at one point was, what real closed fields have integer parts? And our belief was that we would be able to construct a real closed field and somehow diagonalize out, and so it had no integer parts. But a surprising and very beautiful result of Marie-Hélène Morgue and Jean-Pierre Risser is that every real closed field has an integer part. It's a fairly difficult theorem as well, I think. Ended up having useful consequences in studying models of real exponentiation as well.
Dave, can I just interject something very quickly? It's not very important, but I just want to say that this whole seminar that we have, actually the logic workshop started sometime in the 80s, well, it couldn't be in the 80s, early 90s, where Hans Schouten gave the longest lecture ever, and it was on Morgue-Risser theorem. He explained things to us then.
Yeah. I could believe that. I think at some point I gave a one seminar version of this too in the.
Right, I remember that. It was much shorter.
Yeah. Okay. Sorry, I'm a little trouble advancing my slides. Okay. So the question is, so every real closed field has an integer part. When does it have a real closed part, an integer part that's a model of PA? Well, of course, Archimedean ones do. But there's a theorem of from 2012 of Paolo D'Aquino, Julia Knight, and Sergei Starchenko that gives a characterization that if you have a non-Archimedean real closed field and you take an integer part that's a model of PA, then it's actually recursively saturated. Sorry, the field, the field is recursively saturated. And this is done by using some minimality and some coding in the model of arithmetic. Now, conversely, if I had a resplendent real closed field, then it's easy to see that has a Peano arithmetic integer part. And if we also assume countability, recursive saturation and resplendence are the same. So this gives a characterization for countable non-Archimedean real closed field. There's going to be an integer part that's a model of PA if and only if the field is recursively saturated.
Sorry, can I just ask a dumb question on this note?
Sure.
Is it clear, I mean, in this first theorem that you have on the slide, I mean, is it clear, is it true that the integer part that is a model of PA is itself also recursively saturated in this case?
No, because I can start with any model of Peano arithmetic, take its fraction field, take its real closure, and that'll give me a real closed field with a PA integer part. So any model of PA can arise this way, but the only real closed fields that arise this way are recursively saturated ones.
Okay, thank you.
Okay, so one might wonder to what extent.
Sorry about that, but this what Corey was asking. But will there be another one that is recursively saturated? I guess in the countable case it will.
Yes, in the countable case, right?
Yes.
It'll be anything that's elementary equivalent, I think, or anything with the same standard system, I guess.
Yeah, I mean, because I could take a recursively saturated model of the pair with the same standard system in the countable case at least. Okay. So is anything true in the uncountable case? So the first thing I want to argue is that knowing you have some amount of uncountable saturation isn't enough to get you a good integer part. And this is one of my favorite constructions. So I start with G in ordered abelian group. Let's see. Well, this makes sense for any ordered abelian group, but let's assume it's divisible. So that every element you can always take, for any element G, you can always find a G over N. And I want to form Hahn series by taking formal power series. F is the formal sum over all G in the group of AG T to the G, where A to the G is a real number, and T to the G is just a formal symbol, where you multiply T to the G times T to the H by taking T to the G plus H, where G plus H is in the group. Now, it's easy to add series like this, but not so easy to multiply them. So what I want to do is make an assumption that support is well-founded, so that if you look at the set of G such that AG is not 0, that's a well-ordered set. And now the standard way of multiplying two power series, it gives me a well-defined multiple of two of these Hahn series with well-ordered supports. And now this is the part, the construction up to this point works for any ordered abelian group. For this statement, I really need G to be divisible. If G is divisible, this is a real closed field. I mean, if I take the coefficients from any real closed field and then I take a divisible group G, I would get a construction that's a real closed field. There's a natural integer part to this. If I look at things of the form f plus n, where n is a standard integer and the support is negative. So the negative support things are sort of pure infinite elements. Then that's going to be an integer part of this. So this is a way of, you can always get models of open induction sitting in that are integer parts of Hahn series field. And these tend to be as far away from PA as possible usually. So if I just build an integer part this way, let's say I take the element t, or let's say t to the minus 1, that's some infinite element, and square root of 2 times t to the minus 1. Those are both elements of this integer part, and their quotient is square root of 2. So this is a way of getting models of open induction where the square root of 2 is rational. And then an easy construction goes that if I start with a saturated group, a kappa saturated group, the Hahn series field I'm going to get this way is going to be kappa saturated. And what I want to argue is that, okay, I've showed you one way to get an integer part. There might be lots of other ways, but I can't get an integer part of a Hahn series field that's a model of Peano arithmetic. So for all kappa, this gives me kappa saturated real closed fields with no Peano arithmetic integer parts. And the argument here is kind of simple, modulo theorem. Suppose I have a model of PA that's an integer part. then I can get an exponential from R into its quotient field. Just use the usual exponentially. I mean, I can exponentiate the positive elements of R in the model of PA, and that gives me a way of exponentiating the negative in R. And now I can extend this to whole Hahn series field as follows. So a general element of the Hahn series field looks like an element of the integer part plus a real number between 0 and 1 plus an infinitesimal. And now I can exponentiate each of these things. So 2 to the n we exponentiate in the model of arithmetic. 2 to the r we take the normal exponential in the r. And in the Hahn series field, I can formally exponentiate an infinitesimal by just taking the Taylor series for 2 to the x and plugging that in. And this is well defined and satisfies the usual laws of exponentiation. And this gives me a total exponential on the Hahn series field. But there's a theorem of Kuhlmann, and Schalat from 97 that a Hahn field can never have a total exponential. So this gives me a contradiction here and gives me examples of kappa-saturated real closed fields. The Kuhlmanns here involved here, Franz Victor and Salma. I mean, there's actually when I was looking at the date for this, I realized there's another Kuhlmann-Schalat paper, but not the same Kuhlmann. I mean, only one of the same Kuhlmanns. Okay. What about resplendence? Could it possibly be true that anytime you have a PA integer part, the model is resplendent? Well, the answer is no. And let me start with something that'll come up, a thing we'll need later in the talk. So take a non-Archimedean real closed field. And then in it, I want to form O, the convex hull of the natural numbers. So this is always going to be a valuation ring. Any element of the field is either in O or its inverse is in O. The maximal ideal is the infinitesimals. And the value group of the field is just, the multiplicative group mod the units. I mean, this is sort of the standard valuation constructions. And just for an example, if I started with the Hahn series field, the value group is G. So this is sort of an algebraically meaningful thing that's associated with the group. Now, if I happen to start with a resplendent field with value group G, then any interval in G is going to be the same cardinality as G, which is going to be the same cardinality as the field itself. I mean, this is one of the nice things. Resplendent things, usually you don't get two cardinal models of any kind. Okay, and we'll see that there are going to be models of PA where this is not true of the real closure. Here's some notation that we'll use later on. Q of M is going to be the quotient field of M. R of M is the real closure of the quotient field. And gamma of M is the value group of the real closure. And when I take an elementary extension, there's an easy calculation that shows that the value group of the original field is going to be a proper convex subgroup of the value group of the elementary extension. In particular, if I take an ω1-like model of PA, where I build it by some ω1 length chain of end extensions, there are going to be lots of proper convex subgroups that are countable. So if I start with an ω1-like model, I know the real closure can't be resplendent. So more or less, this is where I gave up on these questions. So it doesn't, having a PA integer part isn't equivalent to any amount of saturation, and it's not equivalent to resplendent. I mean, a question is there any natural characterization here of the models, uncountable real closed fields that have a PA integer part? I'm not even sure what a candidate for what such a thing would be now. Okay, so I'm going to move on to a slightly different question. So just like in arithmetic, there's a notion of standard system for any real closed field, but in particular, I want to look at recursively saturated ones. Let K be a real closed field. take an element in O. So think of O as sort of the finite parts of the real closed field, the things that are close to real numbers. So any element of O has a standard part, a real number such that A minus standard part of A is infinitesimal. And I can look at the standard part, the set of all standard parts, let's call that little k. And in fact, this is isomorphic to the residue field of the model. So this is really canonical. It's, algebraically, it doesn't really have anything to do with non-standard analysis. It's really just an algebraic construction. And then I'm going to form the standard system of k to be the Turing ideal generated by little k. If I have a recursively saturated model, the standard system is going to be will be a Scot set, and up to coding, it's exactly the residue field. Any n-type realized in k is going to be coded as an element of the standard system, and any partial type coded in the standard system that's finitely satisfiable is actually realized in k. So B and C together is Wilmer's notion of saying that k is standard system k saturated, S saturated for this particular Scot set. And Dukino and Knight Sarchenko also noticed that if you start with a recursively saturated real closed field with a PA integer part, then the standard system of M is exactly the standard system of K. There's really only one notion of standard system here. And this more or less follows from the fact that the fraction field of M is dense in K. I guess you also use the weak recursive saturation of, any model of PA is saturated, recursively saturated with respect to bounded complexity types. Okay. So in particular, if I start with a model of PA, the standard system of the real closure is exactly the standard system of M. So if I start with countable models of PA that have the same standard system, the real closures are isomorphic. So this is sort of an interesting question. I mean, you start with a model of PA and you pass to its real closure. What information about the model of PA do you still have? One thing it says in the countable case, in the countable case, the only thing you have left in the real closure is the only information you have left in the real closure is the standard system. You forget the theory in particular. Okay. Let's see, we're gonna come back to this in a moment, but I want to spend a few minutes on a digression. So in one of the oldest open questions about models of arithmetic is the question about representing Scot sets. I mean, if you have a Scot set, you want to know, is there a model of arithmetic that has that Scot set? Or even stronger, is there a recursively saturated model of arithmetic that has that Scot set? Of course, we know it's true in the countable case. Knight and Adele showed it's true if the standard system has size at most aleph 1. So under CH, it's true. But is this true outright? So you can, anytime you have a theory, you could ask the same question for recursively saturated models of that theory. And I want to ask that for recursively saturated real closed fields. And Alf Dolic, Julia Knight, Karen Lang, and I showed that for real closed fields, you can always represent Scot sets as standard systems of recursively saturated real closed fields. Mm. Let me state the main lemma for this and just argue. I mean, we thought this was going to be hard, but in the end, it's actually a very easy result. Suppose I have a real closed field. So I'm just going to build this by realizing types one at a time until I'm done. So at some stage, I'm going to have a real closed field K with the restraint that every type realized that is in the standards in the Scot set S. And I have some type that's in S that's finitely satisfiable, so I want to realize it. I need to show that there's a B that realizes it. So if I adjoin B and take the real closure, I still have this property that everything realized is in S. So this seems too good to be true. And this is the kind of, I made a comment to one of my students at one point that when I'm refereeing a paper and I see a lemma like this, I always look and figure out if there's a problem, it's going to be here. When you're trying to realize some types while omitting others, this is sort of one of the hardest things to do usually. Here, ω1-mality makes it much simpler. So again, here's the standard setting. I've got a real closed field K. Every element, every type realized is in S. I've got some type in S that's consistent and I want to realize it. Okay, one possibility is I've already realized that type in K, in which case there's nothing to do. If not, what does the type do? A one type over a real closed field gives me a cut in the real closed field. If I look at an extension and that type isn't realized, that means there's nothing in this cut in the new extension. So this cut extends uniquely to a cut over the bigger real closed field. So there's a unique type over K that extends P, and I'm just going to take any realization of that and claim that works. So what I need to show that it works is that for any element of the field K, any tuple from K, if we adjoin B to that tuple, that type is still in S. Okay, and the next part will look mysterious as I write it down, but I have a picture on the next slide. Okay, so I have some formula C of V C bar, and I need to know whether or not this formula is true of B. So the claim is that I can find Skolem functions, zero definable Skolem functions in real closed fields, such that the element B is in the interval between f of A and g of A. So this is a fact that's known by the type of B over A. And that the truth value of psi doesn't change between F and G. Okay, well, if I can do this, let's assume this for the moment, and then I'll draw a picture on the next slide that makes this plausible. Then to decide whether psi holds of B in C bar, I just search to find Skolem terms F and G such that these two conditions are true. And knowing the type of BA and knowing the type of AC, I can find these terms F and G. So I can do that computably at S. And then I can just decide whether or not psi is going to be true of B at C or not. So that's the strategy. And here's my high-tech picture. So I've, on the top line, I've drawn the real closure of Q adjoin A bar. So my type is over there and it corresponds to this cut. On the bottom, I've drawn the field K. My type still corresponds to the same cut over K. And I want to look at the formula psi with parameter C bar. Because I'm in a real closed field, this is just a finite union of points and intervals. Okay, this is where ω1-mality comes in. So, and these intervals have endpoints definable from C. So I can find two elements, D1 and D2, one on each side of this cut, such that the truth value of psi doesn't change on the interval D1, D2. Okay, that's the whole argument here. And now I just have to search to find the Skolem terms F and G. Oh, sorry. Search to find the Skolem terms F and G such that these conditions on the bottom of the slide are true. And that'll give me the answer here. So this is actually fairly easy. Much to our surprise, once we'd done this, we saw the same thing's true for Pressburger arithmetic. So if you take a Scot set, I can find a recursively saturated model of Pressburger arithmetic that has that Scot set. And the argument ends up being very similar. You don't have ω1-mality in Pressburger arithmetic, but you have what's called quasi-minimality, which is somewhat similar to that. More or less, it comes down to the fact that types are determined by certain order conditions and divisibility conditions. And then you prove a slightly more complicated version of the last lemma, where the order conditions you work with the same way, and then the divisibility conditions end up being kind of free. Again, going back to the early 80s, Knight and Adele had proved the same thing for the theory of Z+, and they'd asked this question about Pressburger. So, I mean, here are two algebraic structures that are associated with models of arithmetic where the Scott set problem is true. There's one other question that, in the same vein, that I don't know the answer. And that's, I mean, suppose I start with a model of PA and I take a non-standard prime. I mean, Paolo was talking about these constructions a few weeks ago in the seminar. If I mod out by the non-standard prime, I'm going to show that you get a recursively saturated pseudo-finite field, an infinite model of the theory of finite fields. And that, you know, up to elementary equivalence, any pseudo-finite field of characteristic 0 can arise this way. So the question is, does every Scott set arise as the standard system of a recursively saturated pseudo-finite field? The model theory of pseudo-finite fields is relatively nice. You don't have a full quantifier relation, but you have a quantifier relation down to nice simple existential formulas. You don't have prime models, so that makes it harder. But this is, I think, a natural, interesting question. I mean, one can also ask quite similar questions about say, theory of the p-adics. Again, you know, that's something that's associated to the model of arithmetic. You can associate a model of a p-adically closed field for any p by taking the p-adic closure of the rationals, and then you might wonder the same question there. I mean, none of these seem to be giving us any actual help in answering the original problem about representing Scott sets in PA, but I kind of like these. Okay, let's go back to the main theme. So the question we came up with was, okay, we know that for countable models, knowing the Scott set determines the real closure up to isomorphism. Could this possibly be true for, you know, in any kind of uncountable cases? And the place we thought most likely you would try and find this phenomena, we look at ω1-like models. And the first result gave us some hope. So Charlie Steinhorn and I proved that if you take two ω1-like models with the same standard system, then we couldn't show the real closures were isomorphic, we could show the value groups were isomorphic. So you start with PA, the model of PA, you lose information going to the real closure, you lose some more information going to the value group. And in fact, you lose everything going to the value group, you lose everything except the standard system. So that gave us hope, but in fact, it's not true at all. So with Jim Schmerl, we have the following result: that if that in fact I can find the maximum number of recursively saturated ω1-like models that are as alike as possible. So in fact, they're infinity omega equivalent for alpha not equal for alpha. Okay, but that pairwise, the real closures are not isomorphic. So I can get the maximum number of non-isomorphic real closed fields, all coming from models of PA with the same integer part, with the same standard part. So the history of this is Charlie and I proved this originally, but under the assumption of diamond, by an argument that has some of the same ingredients that come up later. Then somehow the diamond argument was used in a kind of stupid way, but one that we couldn't get around. I gave a seminar on this, a talk on this at a meeting at Wesleyan when Jim was in the audience, and I explicitly said during the talk that I wanted to give this talk with Jim in the audience so he could tell us how to remove diamond, which he did. So I want to talk about that. We'll talk about both of these today. So let me first talk briefly about the value group case. Okay, so I have ω1-like models of PA the value groups are isomorphic. If the standard system is the same, the value groups are isomorphic. In particular, it says there are only continuum many isomorphism types of value groups, which is sort of interesting. And our original proof was just brute force. You have these two ω1-like models, you break them up as continuous ω1 chains of countable models. And we showed basically by brute force that you could, if you have an isomorphism at the first step, then you can continue that at every step. You can always extend the isomorphism. I mean, excuse me. If I was just doing this with chains of divisible ordered abelian groups, it wouldn't be true. And the way you would make it not true is by sometimes you would put as you added infinite elements compared to the model you had before, sometimes you'd put in a least Archimedean class of new elements, and sometimes you wouldn't. With models of PA, you never put in a least Archimedean class, and that seems to be that's enough to actually get the whole isomorphism going. Okay, so that can be done by brute force, but there's a more elegant way to do it, and it sort of gives you a picture of what the value group is. It says that if you have a non-standard model of PA, then up to reversing the order, the value group is really just, really intrinsic to the model of PA. You don't have to go through the real closure. You just take the additive group and mod out by Z. And this is very easy. I mean, take an element of the real closure. I can find a natural number n such that its x looks like 2 to the n times r, where r is between 1 and 2. But if r is between 1 and 2, then these elements have the same value if and only if the exponents only differ by a standard integer. Basically, having the same value means I could multiply by a standard real to get above 1, below 1 to above 1. Okay, and that if I want to take the value of a product, it's going to be the sum of the values. And this just says it reverses the order. And then there's another old theorem of Victor Harnack that says if I have ω1-like models of PA with the same standard system, then there's the ordered additive groups are isomorphic. So the value groups are necessarily going to be isomorphic. So this is a cute proof of that result that we've done by brute force, but using this result of Harnack is really very easy corollary. Okay, so the rest of the talk, I want to describe the result with Charlie and Jim on ω1-like models of PA, trying to construct examples where the real closures are all non-isomorphic. So let me discuss the ingredients. Some of these are sort of classical things about PA. So recall that in a model of PA, if I take an elementary end extension, it's conservative if for any definable set in the big model, if I intersect that with the small model, it's definable in the small model. And two of the classical facts on models of PA is that every model of PA has a conservative elementary end extension. I mean, this comes from the usual McDowell-Specker argument, but also that if I take a countable model of PA at least, it's going to have a non-conservative elementary end extension. So for countable models, I can build conservative end extensions and I can build non-conservative end extensions. This helps us build rather classless models. So in a model of PA, recall that a class is just a subset of the model such that every initial segment of it is definable. Okay, so if I had a definable set, it would have this property. And we say that PA is rather classless if every class is definable. And then there's a standard construction of ω1-like rather classless models, take an elementary chain of countable models, an elementary chain of elementary end extensions, and we can code in a stationary set by, if alpha is in the stationary set, I take a conservative extension. If alpha is not in the stationary set, I take a non-conservative extension. And in the end, this way, I build a rather classless model. Okay, the third ingredient is something that's new here. It's sort of, I call it the last chance lemma, that if you're building end extensions of model of PA, and you're looking at types of the real closure, you have one chance to realize a type. So take a one type over the real closure of the first model. If I can realize it in the real closure of the third model, then in fact, I've already realized it in the real closure of the second model. And in fact, not only in the real closure of the second model, in the quotient field of the second model. Okay, so this lemma is going to be one of the ways we try to control the real closure by controlling the models of PA. So suppose I have a realization in the third model. I may as well assume the type is bounded by an element of M. If it's the type at infinity, well, then we know it's realized in M prime. So that's no interest. So let's assume that the type is bounded. And just the way that types work, again, types in ω-minimal structures, so in real closed fields, look like cuts. So if I take anything in M prime or M double prime that's bigger than M, and I take something that's really close to the realization of the type, it's also going to be a realization of the type. So without loss of generality, my realization of the type is going to be in the fraction field of the second model. Now I'm going to pick some D, a denominator, in the first model. Again, a denominator that's bigger in the second model, it's bigger than the first model. And then I just want to find out, where does A sit with respect to fractions that look like the denominator D. So there's going to be some C in M double prime, such that A is between C over D and C plus 1 over D. But C is less than M times D, so it's bounded by something in M1, M prime. So C is actually going to be some element of M prime. And C over D, because it's closer to A than anything, the distance is smaller than anything in the residue field of, in the fraction field of M prime, it's also going to be a realization of the cut. So this is a useful tool in our construction. Okay. And then the last ingredient, this is what Jim told us about, is the notion of Scot completions. Take an ordered field. Now I want to look at an initial segment of the ordered field. So think of it as a cut in the field. We say it's Dedekindian if whatever element I add to I, if I add any positive element to I, it shifts me out of I. So nowadays, these kind of cuts are called non-valuational. Basically, what happens is if you don't have this property, if you have a non-Dedekindian cut, it more or less comes from some kind of valuation ring. Think about what kind of thing, if I have a non-Archimedean real closed field, what kind of thing won't have this property? Well, if I actually have if I take just the finite elements, then for the finite elements, if I add a finite element to the whole set of finite elements, I still just get the finite elements back. So that's an example of a non-Dedekindian cut. And these tend to be associated with evaluation rings. And I say that an ordered field is Scot complete if any Dedekindian initial segment actually has a least upper bound in the field. So of course, real closed fields are Scot complete, but the interesting thing happens in non-Archimedean fields. And Scot showed that anytime I have an ordered field, there's a unique, I guess unique up to unique isomorphism field, Scot complete field that extends it, in which the original field is dense. Moreover, he showed that if I started with a real closed field, then the Scot completion would still be dense, would still be real closed as well. Now, Jim related these to models of arithmetic in the 80s. Okay, so if I start with the model of PA, I let the Scot completion of M just be the Scot completion of the quotient field. Jim used these to answer some questions about ordered fields, some complication of ordered fields and sort of the set theory of ordered fields. But an easy argument is that if I start with the model of PA, the Scot completion of that model is real closed. And he also showed that there's a tight relationship between the Scot completion and the classes of the model M. And it comes as follows. Let A be a class. I can find a cut in the model, or a cut over the quotient field by looking at the X that are less than the sum over A of 1/2 to the A plus 1, where I bound these A's by some B for B and M. And as I vary B, this is going to give me a cut in the model. So you think about, intuitively, you take the infinite series over all of A of the 1/2 to the A plus 1. So you look at the things that are less than that. Jim observed that if you have a class, that this initial segment is Dedekindian. And moreover, if you take any Dedekindian initial segment that's between 0 and 1, then it arises this way. So this gives a way of identifying the Dedekindian cuts, or the part of the Scot completion that's between 0 and 1 with cuts in the model. Okay. So those are the ingredients. And now I just want to describe the basic construction. So we're going to start with a fixed model of PA and take a stationary subset of ω1. And I want to construct a chain of models as follows. And I'm going to do it the same way I build a rather classless model. I make, at limit stages, I take unions, and at successor stages, I take conservative extensions if and only if alpha is in the stationary set. So I code the stationary set into the model of arithmetic. And what we'll see is that that this is somehow coded into or intrinsic to the real closure as well. Okay, so then the model I build is just the union of the M alphas. Okay, so by the lemma on rather classless models, this is rather classless. So all the Dedekindian cuts are definable. Okay, they are, because all the Dedekindian cuts correspond to classes, and all the classes, the only classes are definable sets. So the Scot completion is also of size L1. So I can choose another continuous filtration of the Scot the Scot completion of mx as well, where each of these is countable, and at unions, at limits, I take unions. Okay. So I have a filtration of the model, and I also have this filtration of the Scot completions. The main lemma says that if I have two stationary sets x and y minus x is stationary, then the real closures are not isomorphic. So that somehow the real closure retains somehow this information about the stationary set. Okay, so we start this like anything. Suppose I have an isomorphism between the real closures. Then that's going to extend to be an isomorphism of the Scot completions. So let's just say I have an isomorphism of the Scot completions of the two, for the two models that restricts to being an isomorphism of the real closures. And now basically what I do is I write down 6 interesting club sets, and I can find an alpha that's going to be in Y that's not minus X, it's in all of these clubs. So I look for an alpha such that sigma restricts to give me an isomorphism between the real closure of M alpha and the real closure of the real closure on the X side and the real closure on the Y side. I want, I pick my alpha so that S alpha of X is real closed, and that this sigma is an isomorphism between S alpha of X and S alpha of Y. Okay, everything in the Scot completion with respect to X or with respect to Y is definable. So I want to make sure that for Z, either to X or Y, that S alpha is all of the that every Dedekindian initial segment, that S alpha is exactly the collection of Dedekindian initial segments that are definable over the model of arithmetic up to that point. And finally, I want to make sure that if anything in S alpha of Z ever gets into the real closure of M of Z, then it's already in the real closure by stage alpha. And again, this is the usual yoga of these constructions. I mean, these properties I want are all true on closed unbounded sets. So I can find something in my stationary set Y minus X where all of these things are true. Okay, so just to continue to finish the proof. Sorry, this slide is rather dense. Okay, so my alpha is in Y but not in X. So M alpha plus 1 is a conservative extension in M alpha. But on the Y side, I have a conservative extension. On the X side, I have a non-conservative extension. Okay, so on the X side, I can find some definable subset of M alpha plus 1 of X. So when I restrict to M alpha of X, it's not definable. I take B, any element of M alpha plus 1 that's larger than M alpha of X. And I form the sum X to be the sum over elements of A that are less than B of 1 over 2 to the A. 1 over 2 to the A plus 1, I probably want to say. Okay, so we know this is a non-Dedekindian cut. And this X, I can basically do this sum inside the model of arithmetic M alpha plus 1. So this is in the quotient field of M alpha plus 1 of X. Okay, but this is a non-Dedekindian cut over M alpha of X. Or no, sorry, I'm sloppy here. I should say this is a Dedekindian cut, but it's a non-definable Dedekindian cut. Okay. So by my condition on the S alphas, every element of S alpha is definable over M alpha. The cut of this element is not definable. So no element of S alpha of X realizes this cut. But I have this isomorphism sigma. Under sigma, this will give me a new cut that's not definable on the Y side. But on the Y side, I've taken a conservative extension. Oh no, sorry. Just because I have an isomorphism between S alpha of X and S alpha of Y, no element of S alpha of Y realizes this. Okay. But I have realized on the X side, I have realized this type. So somewhere in the real closure of M of Y, I'm going to have to realize this type again. Okay. But now by the last chance lemma, the only place, if I'm going to realize this type ever, I have to do it immediately. So there's some element in the fraction field of M alpha plus 1 that realizes this type. But now I'm going to get a contradiction because on the Y side, I've taken a conservative extension. So the only cuts I can realize on the Y side are going to correspond to things that are definable in M alpha of Y. But then by the choice of the S alphas, again, by the choice of these club sets of the choice of alpha, S alpha of Y is exactly the Dedekindian cuts that are defined over M alpha of Y. So that says that I have to have this so that the realization of this type is going to be actually in S alpha of Y. But as I argued in the middle of the slide, that can't be true because I have the isomorphism between S alpha of X and S alpha of Y. Okay, so this is very quick. The paper's on archive if you want to look at this argument more carefully, but it's very nice. And somehow the Scot completions are allowing me, somehow in general, you don't have much relation between the real closure and the model of arithmetic. The Scot completion, because everything else is definable at some stage, you have more of a connection between the Scot completion and the model of arithmetic. And ultimately, that's what we look at, that's what we need at this stage. Okay, so that's the main lemma. The only thing I owe you is recursive saturation. I didn't do anything to make these things recursively saturated. But in fact, you don't have to. This is somehow the beauty of satisfaction classes, that the recursively saturated part almost comes for free. Again, if you know that all the theorems in the book, but the book I mean, of course, Roman and Jim's book, all the theorems from the book that I've used up until this stage work not only for PA, but if I had PA relative to a predicate or relative to a number of predicates. So, and the trick is just this one. We say that a subset of M is a partial satisfaction class if for any formula phi, if I take the Gödel code of phi and some tuple code for a tuple from the element, from the model, that's in the class if and only if the formula is true of that tuple. So that's the notion of a satisfaction class. It's just a definition of satisfaction that works for all standard formulas. We say that the satisfaction class is inductive if it satisfies the induction axiom where I just adjoin a unary predicate for gamma. And so PA star is just, you add a unary predicate and you ask for arithmetic with induction, including, for formulas including this predicate. Okay. And let's see, an overspill argument shows that if you have an inductive satisfaction class, then the model has to be recursively saturated. It's also easy to see that if you had started with a resplendent model, then there's going to be an inductive partial satisfaction class. So taken together, these things tell me that a countable model is recursively saturated if and only if there's an inductive satisfaction class. As I said, all of the results we proved before about PA go through for PA star. I mean, by that I mean the results about rather classless models, the existence and non-existence of conservative and non-conservative extensions. So basically, we start with, go back and do the construction again in a language with a unary predicate where my base structure has a partial satisfaction class. Then when we finish, all of the M of X will be recursively saturated. Then another sort of classic fact is if I take no, this is not right. So if I take recursively saturated, elementarily equivalent ω1-like, I need to say add ω1-like here, models of PA that have the same standard system, then they're going to be infinity ω1 equivalent. So this is, I could allow arbitrary conjunctions and I could allow countable quantifier strings here. So these models are, the models I'm building this way are exceptionally similar. I mean that, it takes some complicated forcing to try, under a lot of forcings, they'll end up being isomorphic. Okay, and then finally, the last ingredient is sort of the usual combinatorial set theory, that if that it's not hard to find a family of 2 to the aleph 1 stationary subsets of ω1, such that any 2 differences is also a stationary set. And so using these to build the models, we get the models that we talked about in the theorem. I mean, to prove this, you just take ω1 different disjoint stationary sets, and then you take for any subset of 2 to the ω1, you take the union of all of those. That's sort of an easy argument for this. Okay, so that's the argument, and that's my talk. So thank you very much.
A quick question.
Sure.
About a third of the way through, the name Turing came up, and it was a Turing closure, was it, or? Yeah,
the Turing, I may have said the Turing ideal generated by, so.
Yeah, it didn't come up again, so I didn't look it up on my cell phone.
So I mean, you take a collection of subsets of ω1, or so of omega, and you just look at the Turing ideal they generate. So you close under join, and you close downward under Turing reducibility.
Thank you.